Chapter 8, Combined Loading, Application of Superposition in Combined Loading. Example number 3, Foundation example. So in this example, we do have a rectangular foundation which carries a concentrated load of P. As you can see here, the load P has a centricity, a distance from both x and y axis. So that's Ex and Ey. So what is the condition of Ex and Ey if we want all the foundation to be under compression? So let's talk a bit about the condition of this kind of problem. So if you, the very first things we need to do for such problem is to, like from statics, we just trans move the force to the centroid. So if this is the centroid where the two axes meet each other, that's our centroid, the symmetry of the structure. So if we just move the force concentrated load of P to the centroid and create the opposite of that, because these two should cancel out each other, because in reality we don't have this force at the centroid and we just have the real force over here. So as soon as we transfer the force over here, as you can see, these two forces create a bending moment about the both axes, because we do have a centricity based off both of these x and y axes. So let's see how that goes. And if you, let's see the effect of the bending moment. So if you look at the m created about y axis, it just a clockwise moment, which is a moment is a force times its arm. So that's a moment. My is the force of P times the centricity of x, which provides a bending moment about y-axis. And if you look at the nature of this clockwise moment, you can easily see this kind of moment pushes the point B all the way at the top, huh? and pulls the other side point A at the other end of the foundation. So one can easily say point B is under a two a combined compression force was to the normal force of P applied to the entire area, and the other one is the uh, normal stress created by the bending moment, and that's a effect of bending moment which pushes point B and pulls A. So, and the other moment, if you look at the problem, you can easily see, because there were two eccentricity at the beginning, Ex and Ey, and the other one provide a bending moment about x axis, so that's mx moment about uh, x-axis, and that's the force times Ey. And if you look at this force also, you can easily see the second moment is also pushing point B and pulls the point A. And all this kind of problem, there is a kind of foundation located on the top of a pile of soil. And as you know, soil is a tau, capacity of soil is C plus sigma tangent of phi, and it says soil is strong in compression and it's very weak in tension. So in that sense, point A is in danger. So we can apply a something like a huge force of push to the soil, to the foundation, but as if just by a kind of tension, we just we, there is a risk of separation of foundation from the soil. So soil and most material are uh, good in compression and weaker in tension. So in that sense, our critical point in this foundation is this point A. Let's see how we can approach the problem. So if the critical point, which we already talked about that, and that's A of this foundation, this is point A. If we design our problem in a way, if we locate force P in a distance, that in such case that the point A is under compression, then we have all foundation under compression. So there is no point if the critical point stress is under compression. Means if the critical, the condition of the other point are kind of better than the critical point. So it means if the worst point is under compression, the others are safe. So that's a kind of controlling point for the whole, for entire foundation. Then let's go to combined loading and see how we can have our problem. So to have point A remaining under compression stress, so we have a negative P over A, that's a compression force. At point A, there is a mx times ya over ix. It just wants to, that means this is compression, and this is tension. Due to mx is here, and there is other one, my over iy times xa this time, and it should be less than 0 to keep the entire stresses of A under compression to be in safe zone. So then area is dimension of our foundation, B times L, and then mx is P times EY, P times EY, and if you want to see the effect of mx, need to work with this distance, and that's L over 2. And if you want to see the effect of my, which is P times Ex, you need to go with this dimension. That's B over 2. And is likewise Ix is 112, Ix 112 base L cubed, and Iy is 112 L B cubed this time. And that should be B. If you multiply all the quality by a negative, even the sign turns to other direction. So if you simplify this equation, it just gives us a, so L over 2, 12 is 6, and L is L square. So that's P over BL minus 6 times PEY over BL L square minus P times AX over LB square. This time it should be higher than 0. Yet we can rearrange this equation and more simplified. And so that says P over BL minus, so can have it like again multiplied by, take this part, other part, so that's a minus P. Then again multiply all the equation by a negative. Again the sign is changing, and it just gives us a final equation and condition for Ex and Ey, which is 6 times Ey over L plus 6 times Ex over B. It should be less than 1. Sorry, this is less than 1. So if we just bring this here and divide it by P over BL, it just turns to be 1, and it just divided by PBL. So that's 6 times Ey over L plus likewise P L E 6 EX over B should be less than 1. So this equation is interesting. Note 1. If EX and EY both satisfying the top equation, this equation, stress at point A will remain in compression zone. So that's safe. Because point A is the most critical point in the, because it has the worst situation, because it's under a one compression from the force, but two tension from both moments. So that's the most critical. This is the most safe zone, and the rest of the point is just a kind of combination of a compromising between a push and pull, but this one is the worst condition. So if this one is under compression, if we have an equation in such point A is safe. By safe, I mean under compression, because soil is strong in compression. All the other points are also under compression. So it means no point is under tension. The foundation will not detach from the soil underneath, and that's a good design in terms of foundation. Yet that equation has tells us something more, and above equation, this equation, my bad, this is less than 1, this is less than 1. Above equation is the equation for one of 4 lines of the central rhombus. So if you just develop the other lines, you can create a rhombus in the central part. And the most interesting part is if your concentrated load of P remains in the central rhombus, nowhere. So for example, if your P applies here, if P applies here, applies here, applies here, or anywhere on or inside this central rhombus, it just says your design is safe. All the external part, including point A, all the point of the foundation remains under compression. And if you just your force is coming out of this central rhombus, so in that case, some part of the foundation might be in tension, which is not good. So that's a good uh, design criteria. That's also, we call this rule as the middle third equation in civil engineering. Thank you. We'll solve more problems in next videos.